So this evening we'll be looking at this topic. Okay, gas laws and anesthesia. That's what we'll be looking at. Okay. So we'll be looking at these learning outcomes. We want to define fundamental gas laws. At the end, we should be able to explain how each of these gas law applies to our practice as anesthetics and critical care physicians. We should be able at the end to also interpret clinical implications of gas behavior in storage, delivery, and physiological response. And we should be able to apply the knowledge of these laws to patient safety, equipment management, and anesthesia. All right, so let's just look at these questions. This MCQ. Number one question, are we there? A 35-year-old patient with a known pneumothorax requires helicopter transfer to a tertiary hospital. Which of the gas laws below explains the potential expansion of the pneumothorax during ascent? A. Charles law. 2. Boyle's law. C. Dalton's law. D. Henry's law. E. Avogadro's law. Any attempt from anybody?
B.
Hello?
B.
B. Okay. Why B? Why B? Anybody? Nobody is answering. Why did you choose B?
Boyle's law states that with temperature remaining constant, volume varies inversely proportional to the pressure.
Okay, so during ascent, what happens to pressure?
Pressure goes down and volume increases.
Beautiful, good. Number 2, during pre-oxygenation, a patient breathes 100% oxygen via a non-rebreather mask. Which principle explains the calculation of alveolar oxygen partial pressure? A. Boyle's law. B. Dalton's law. C. Henry's law. D. Charles' law. E. Gay-Lussac's law. Any attempt?
Gay-Lussac's law.
Gay-Lussac's law. Any other answer?
Dalton's law.
Yeah, Dalton's law, correct. Dalton's law. What does Dalton's law state? What is Dalton's law? What is Dalton's law? The total pressure of a mixture of gases. Yeah, go ahead.
Total pressure of gases mixed, the gases exert the same pressure as they would if they were alone.
Beautiful. Good. Okay. A nitrous oxide cylinder shows a full gauge pressure at room temperature. Which property determines how much gas remains? Cylinder pressure gauge, color coding, cylinder weight, vapor pressure, gas density.
C.
C. No, C for you have a PhD in physics, eh? That's good. D. C rather. All right. Can you explain that? Is every other person following? Are we following? Only 36 people here today. Any other person? I mean, Lucifer, can you explain that? Why did you choose C?
For nitrous oxide, Prof, the only way you can get how much nitrous oxide is left inside is by weighing the cylinder. You can't use the gauge pressure.
Yeah, correct. All right. Why? Because the pressure will always be constant because as you use nitrous oxide, the liquid vaporizes to maintain the pressure, the pressure, all right, of the gas. So the gauge pressure may not change, but you measure the cylinder. What is the other name for the cylinder weight? How do we call it again? The cylinder
Tire
weight.
weight.
Tire weight, Oscar, correct, tire weight, all right. But for a ventilated patient in ICU has increasing peak airway pressures despite unchanged tidal volumes. Which property of gas flow most likely account for increased resistance due to turbulent flow? A ventilated patient in ICU has increasing peak airway pressure despite unchanged tidal volume. Which property of gas flow most likely accounts for increased resistance due to turbulent flow? Charles law, density of gas, Henry's law, Darcy's law, Boyle's law.
B.
B, correct. Density of the gas, correct. And anesthetic uses a venturi mask to deliver 40% oxygen to a hypoxic patient. Which principle explains the entrainment of room air into the oxygen flow? Under effect, venturi principle, Bernoulli's principle, Agassiz law, Avogadro's law. Which one?
C. Bernoulli's.
Sorry?
Bernoulli's principle.
C. Bernoulli's principle.
Yeah, it's tricky here. All right, between B and C. Bernoulli's principle explains Venturi's effect. Okay, so what are you choosing, B or C?
B.
B.
I will choose B. All right. How does it work? How does Venturi's principle work? Anyone? Anyone quickly? Venturi's principle, quickly explain. Abdulhamid, are you trying to say something? Okay. We'll get to see it as we go on.
What I know about Venturi principle is that it depends on the aperture in the Venturi that is being used. So the kinetic and potential energy is the same, but after the gas passes through the aperture, the the kinetic energy becomes more than the potential energy. So that's what gives the exact flow of gas that is delivered to the patient.
Okay, good idea. The total energy remains the same. All right. So when you have a flow of gas under high velocity, all right, and you make it to flow through a narrowed aperture, like she said, the kinetic energy remains the same, but the potential energy, the pressure, all right, it drops, and that pressure entrains air All right, it helps to ensure that you have constant oxygen concentration delivered to your patient. Okay, good attempt. A patient undergoing hyperbaric oxygen therapy has a cuffed endotracheal tube. Why is the cuff filled with saline instead of air? Which of the law explains the reason why the cuff of the endotracheal tube is filled with saline instead of air in hyperbaric chamber? Anyone? Is somebody making a call? What's going on? Okay, anybody? Anybody making any attempt? Kamanzi or Pandas? Sorry?
Boy's law.
It's Boyle's law. A.
Yes, explain. How does Boyle's law explain this? How does Boyle's law explain this? You are right. I'll take Boyle's law too, but how does he explain it?
The Boyle's law it states that at a constant temperature, the volume of a gas is inversely proportional to the pressure applied to it. So in this case, if you use the saline, if you use the saline to cuff during the hyperbaric therapy, this will avoid the volume changes.
Yes. All right, you're right. Because hyperbaric chambers, the pressure is high. So if you use air, the volume of the air will be reduced, and you can have a cough collapse. Okay, good attempt. Number 7, at 4,000 meter altitude, the vaporizer said that 3% sevoflurane still delivers the same anesthetic partial pressure at sea level, but the delivered concentration differs. Which law explains this phenomenon? Which law explains this phenomenon? A. Henry's law, B. Dalton's law, C. Boyle's law, D. Gay-Lussac's law, E. Charles' law. Which one?
Answer B. Dalton's law.
Dalton's law. Correct. A patient's inspired gas warms from 20 degrees centigrade to 30 degrees centigrade as it reaches the alveoli. Which gas law explains the change in gas volume? Quickly, we are 20 minutes into the hour. Quickly.
Answer B. Charles' law.
Charles' law, correct. Last 2 questions. A patient with decompression sickness presents after surfacing too quickly from a deep dive. Which law explains the formation of nitrogen bubbles in the bloodstream?
It is still Boyle's law.
Sorry?
Boyle's law.
No, not Boyle's law. Any other person? Any other person? What law explains decompression sickness?
C. Henry's law.
Henry's law, Paula. Henry's law, correct. Number 10, a 4-year-old patient with severe airway obstruction is given Helios, a high flow nasal cannula. Why is Helios effective in reducing airway resistance?
C. Lower density than
C.
Sorry?
C.
Lower density than air.
Correct. C, lower density than air. Good job, everyone. At least we'll have the 8/10. Okay, so we'll follow this outline this evening. By way of introduction, anesthesia involves the administration of various gases under controlled conditions. So a good understanding of the physical properties of gases and how they behave under different conditions is essential for safe anesthetic practice. I'm sure we agree with that. What is a gas? We know that we have 3 states of matter, all right, solid, liquid, and gas. So a gas is a state of matter in which the molecules are always in constant random motion without any fixed volume or shape. All right, some of the properties or qualities of a gas is that it is compressible. All right, a gas exerts pressure uniformly in all directions, and a gas will expand to fill any container into which it is put. So we have 2 kinds of gases. We have the ideal gases and the real gases. The ideal gas follows the ideal gas equation where pressure times volume, all right, is equal to the temperature, excuse me, all right, and an ideal gas, an ideal gas assumes 0 intermolecular forces and they occupy no specific volume. It occupies the volume of the container into which it is placed. All right, real gas, however, deviates from ideal behavior, especially at high pressures and low temperature. Most of the gases we deal with in anesthesia exhibit the real gas behavior, which is important, especially under storage conditions. So there are some excuse me, properties of gases we're going to remind ourselves of. Number 1 is the pressure. All right, this refers to the force exerted by gas molecules over a unit area of container walls. All right, there are different units of measurement. We have atmosphere, kilopascals, millimeters of mercury, and bar. And the relationship between these units is presented below. So 1 atmosphere is equal to 760 millimeters of mercury, which is approximately 100 kilopascal, which is equal to 1 bar. Now, the pressure of gases are important because most gas are stored under high pressure in cylinders. All right, and pressure difference also drive gas flow in our ventilators, breathing circuits, and different oxygen delivery system. All right, the pressure of gases, all right, is important to consider during risk of barotrauma, which can occur with high intrapulmonary pressures. The second property of gases that we're going to look at is the temperature, which is a measure of the average kinetic energy of gas molecules. All right, the SI unit is Kelvin, all right, and the relation between Kelvin and Celsius is presented in the slides. So Kelvin is equal to Celsius plus 273.15. All right, the relevance is that gas increases volume, all right, when, under increased temperature. Vapor pressure and anesthetic gas also depends on temperature. But remember, that is why we have temperature compensated vaporizers. And hypo or hypothermia also can affect gas solubility and metabolism. The top property of gases that are very important to us is the volume. And this talks about the space that the gas occupies. All right, and it's measured in liters or milliliters. Okay, the Boyle's law we talked about, and the Charles law relates, volume with pressure and temperature, as we're going to see. Also, in closed gas spaces, all right, the volume of the gas will expand at altitude due to decreased ambient pressure. All right. The other property of gas we would consider is the density, and we talked about it just now in our questions session. So density is mass per unit volume of gas, all right, and the density of a gas influences the type of flow of the gas through its containers, all right. Helios, which is a mixture of helium and oxygen, reduces airway density, airway resistance, because it has lower density than air. And the flow meters, all right, that measures our flow, the flow rate of our different gases, are calibrated for each specific gas densities. Very other important property of gas is what we know as the critical temperature. All right, and this is very relevant, especially it relates to nitrous oxide. All right, so critical temperature refers to the highest temperature at which a gas can be liquefied by applying pressure alone. So above a gas critical pressure, the gas cannot be liquefied regardless of the pressure you exert. All right, so nitrous oxide, for instance, has a critical temperature of 36.5. So if it is stored, if nitrous oxide cylinder is stored at temperature below this, it will contain both liquid and gaseous nitrous oxide. However, when the gas is withdrawn from usage, liquid nitrous oxide boils to replenish gas while maintaining a relatively stable pressure. And that's why the pressure gauge will not change. However, if the temperature rises above its critical temperature, above the nitrous oxide critical temperature, the nitrous oxide will only exist in gaseous form. Okay, and that's the importance of critical temperature, and that's why it's important for us to keep the nitrous oxide cylinder in very cool storage environment. Okay, the critical pressure, all right, is talked about, all right, the pressure, all right, at which, okay, this is talking about critical temperature, okay? So ethanol, which is a 50-50 mix of nitrous oxide and oxygen, all right? The critical temperature of nitrous oxide is important here, okay? If the mixture is stored at low temperature, the nitrous oxide can separate from the oxygen, all right? And this may, potentially lead to delivery of hypoxic gas mixture, especially during the labor analgesia. And don't forget that the critical temperature of volatile anesthetic agent can also affect the performance of the vaporizers, all right? So temperature changes do affect it, and that's why we have temperature compensated vaporizers. So critical pressure, this is the minimum pressure required to liquefy a gas at this critical temperature. Okay, and this is important because it influences why some gases like nitrous oxide are stored as liquid, while others remain as gases. All right, it also influences cylinder pressure readings and gas content estimation. So the next one is standard vapor pressure, saturated vapor pressure, and this refers to the pressure that is exerted by the vapor of a gas, all right, that is in equilibrium with its own liquid at a given temperature in a closed system. All right, at saturated vapor pressure, the rate of evaporation is equal to the rate of condensation. Saturated vapor pressure depends only on temperature, not on the volume of the liquid or atmospheric pressure. Note that this is important because each volatile anesthetic agent in practice has its characteristic saturated vapor pressure at a given temperature. All right, and this a lot of time determines the design of its vaporizer, as we will see as we go on. Desflurane, for instance, had a very high saturated vapor pressure, so requires a specific heating system. All right, so these are the implications of saturated vapor pressure. All right, the variable bypass vaporizers rely on low saturated vapor pressure. All right, so the saturated vapor pressure must be stable. Otherwise, the inspired concentration for your vaporizers will vary, and this will risk either under or overdosing of your patient with your vapor, your anesthetic vapor. However, desflurane has a very high SVP, like we saw, so requires a heated pressurized vaporizer detects series. Okay, so high saturated vapor pressure means that the gas is, the liquid is volatile at room temperature, while the low saturated vapor pressure shows that the liquid is less volatile, so it's safer for standard vaporizer designs. So let's look at the different the different gas laws. The first one, like we said, is the Boyle's law, which states that at constant temperature, the pressure of a given gas is inversely proportional to its volume. All right, and we can see the graph here. As the pressure increases, volume or decreases, and vice versa. So what are the implications? All right, during normal inspiration, all right, you increase your interthoracic volume, reducing your pressure below atmospheric pressure. Therefore, gas comes in from outside, inside. All right, when you are administering your drugs through your syringe, as you pull the plunger, you increase the volume, and this decreases, pressure, and pressure comes in from the atmosphere. This is what happens with the risk of pneumothorax. As a patient increases, a patient with pneumothorax, all right, at high altitude where the pressure reduces, the volume of the pneumothorax can increase. All right, this can actually lead to tension pneumothorax with hemodynamic collapse. Okay, so for instance, a 40 mm pneumothorax can expand by 16% at 1.5 kilometer altitude and up to 30%, okay, at 2.5 kilometers. So a patient that you are transferring with a pneumothorax, all right, with a helicopter, you must bear this in mind. And because of this possibility, you may want to decompress or do a thoracostomy before air transfer. And this is important as an anesthetist or critical care physician, or a patient that you are called to airlift with pneumothorax, you need to explain to the surgeons they need to do a thoracostomy, or else the volume of the pneumothorax will expand following Boyle's law at higher altitude. Okay, and also hyperbaric, we mentioned the saline is used instead of air in the ETT cuffs. All right, this to prevent cuff collapse, because at high pressure, if you use air, the air in the cuff will reduce, and that will cause cuff collapse. All right, for the patient you're trying to protect the airway. So the second law we're looking at is the Charles law, all right, which states that at constant pressure, the volume of a gas is directly proportional to its temperature. All right, so as temperature increases, volume increases. Okay, and this is the explanation. Okay, so look at it. In gas cylinders, for instance, let's use a nitrous oxide cylinder. All right, as nitrous oxide vaporizes, it absorbs latent heat, cooling the remaining liquid. So a drop in temperature reduces vapor pressure, causing a temporary fall, all right, in gas pressure. But note that because the pressure gauge does not indicate the amount of liquid remaining, all right, the tire weight of the gas cylinder becomes important. And one of the safety features of our gas cylinder is that every gas cylinder has a tire weight attached to it. So if you subtract the current weight, all right, from the tire weight of the cylinder, you can determine the amount of liquid nitrous oxide that is remaining in the cylinder. Okay, You can see that in the picture on the right side of the screen. All right. Another clinical implication of Charles' law is that, all right, if you store oxygen at room temperature, especially in the ICU environment or during transfer, the delivered volume will be lower than expected. Even if you have the same flow meter settings, maybe you set it at 4 liters per minute. But because of the reduced temperature, the volume of oxygen being delivered will be lower. All right. And this becomes very important, especially during low flow anesthesia or during precisely controlled therapies, especially pediatric anesthesia. So you need to understand the impact of temperature on the volume of oxygen that is delivered from your cylinder. All right. It does not just rely only on the flow rate, but on the temperature change. All right. During pulmonary function tests, all right, we should always correct our results with the body temperature, pressure, and saturated conditions. Why? Because as the patient exhales, all right, the air comes out is warm and saturated at the temperature of 37 degrees Celsius. So as it goes into the spirometer, which is at room temperature, all right, the air cools down and it contracts, which leads to a smaller volume being measured by your spirometer, all right, compared to the actual lung volume. So most spirometry results are usually corrected for the body temperature, pressure, and saturated conditions. All right. Charles law is important in convective heat loss. All right. You know, when the warm air close to a patient, all right, rises, it becomes, because when the air is warmed, it becomes lighter, all right, and it's replaced by cooler air, creating a continuous heat exchange. So, and this is a major contributor to interpretive hypothermia. So because of Charles' law, you need to also ensure you have active warming strategies, all right, by your first air warming blankets we mentioned the other day, warm IV fluids and all that. So this is to mitigate convective heat losses as explained by Charles' law. All right, we mentioned this before. So gas expansion with warming. Inspired gases increases in volume as they warm from room temperature to body temperature. So for instance, if you have a 500 meter volume at room temperature, this can expand to 530 mil in the lungs where you have, 37 degree body temperature. And for temperature measurement, remember that, the glass thermometer, all right, uses the impact of heat on gas volume. So the third law we're looking at is the Gay-Lussac's law. I'm sure we all remember this in chemistry or physics. All right. At constant volume, the pressure of a gas is directly proportional to its absolute temperature. So at constant volume, the pressure of a gas is directly proportional to its absolute temperature. All right. Clinical implications, especially fire hazard. So if you heat a cylinder, a full cylinder, the pressure of the gas increases, and this can cause gas explosion, all right, whether in the storage or in the OR. The same thing, a cold cylinder will show decreased pressure, not necessarily because you have less volume, but because of the lower temperature. So this is important, especially with our gas cylinders. We mentioned this, all right? Most cylinders contain fixed volume of gases. So if the cylinder temperature increases, the internal pressure of the gas will also increase, leading to the risk of rupture. And the converse is the same. So cylinders must be stored in cool, well-ventilated areas away from heat sources to prevent dangerous pressure rises and explosion from rupture of the gas cylinders. All right, Avogadro's law. Avogadro's law states that equal volume of gases have equal number of molecules at the same temperature and pressure. So equal volume of gases have the same equal number of molecules at the same temperature and pressure. All right, and this is useful, especially, let's look at the clinical, all right, usefulness. So we can use it to calculate the accurate estimation of gas content, okay? And I just did here, I brought a practical scenario. For instance, if you have a 6-hour or 4-hour procedure, or maybe you want to transport a patient who is on oxygen on a 4-hour journey from the referral hospital to the receiving hospital. How do you calculate the number of oxygen cylinders you need? All right. So the first thing you need to do is to determine how much of oxygen am I going to give this patient to be able to achieve my predetermined SpO2. So for instance, now, if you say at 4 liters per minute of oxygen, you can get SpO2 of 95 and you're happy. So we need to know how much of oxygen do you need for the 4-hour trip. So you need to calculate that. So for a patient or a journey of 4 hours or a procedure of 4 hours, and you are using 4 liters per minute, the total oxygen you will use will be now around 60 liters. So the second thing you need to consider is what cylinder size are you having? Do you have? Now, most of the time we have the E cylinder with us. So the cylinder internal volume of the E cylinder is about 4.8 liters at the cylinder pressure when it is full at 2,000 pounds per each. All right. So at saturated temperature, all right, at standard temperature and pressure rather, all right, gas volume will be pressure given this formula, and you calculate you're going to need about 653 liters. So we have 653, but when you convert it, all right, you're going to have 600 liters of oxygen in one cylinder. So the next thing you're going to do is compare the available oxygen and the required oxygen. You realize that you require now around 60 liters of oxygen for at 4 liters per minute flow rate for that 4 hours duration. You realize that one E cylinder full of oxygen will not be enough. And this is important for planning purposes and to prevent untoward complications. We've seen patients who transported and we realize that before the ambulance gets to the receiving hospital, oxygen has run out and the patient become hypoxic, and sometimes just at the point of dropping the patient off, you realize the patient had cardiac arrest or the patient had died, not knowing that oxygen had failed because of lack of proper planning. So the ideal gas law, all right, talks about the product of pressure and volume of a gas is proportional to the number of moles and absolute temperature, all right? So you have the universal gas constant and all of this. The ideal gas law combines all the gas law in one equation. So the next gas law we're looking at is the Dalton's partial pressure, Dalton's law of partial pressure. All right. So there are two ways we can define it. Number one is that the total pressure of a mixture of gases equals the sum of the partial pressure of the individual gases, or the partial pressure of a gas in a mixture of gases equals to the pressure it itself will exert if it alone occupies that cylinder. Okay. And the clinical application is there are so many clinical applications. Dalton's law, all right? So number one is in oxygen delivery, all right? In an anesthetic circuit, the FiO2 and the total circuit pressure determine the partial pressure of oxygen that you deliver to the patient. So it's not just the FiO2, okay? For instance, you may have the FiO2 of 100, all right? But if the barometric pressure drops, for instance, at high altitude, your alveolar partial pressure of oxygen will also drop, all right? And this will lead to hypoxia. So it's important that you pre-oxygenate your patient and you monitor your FiO2, all right? You may need to increase your FiO2 to ensure that your alveolar partial pressure is maintained. All right, Dalton's law of partial pressure is also very important in the anesthetic, to measure the depth of anesthesia. Okay, we know that the depth of anesthesia is usually measured by the partial pressure of the anesthetic in the brain. Okay, so vaporizers always deliver a specific volume percentage, but the desired effect correlates not with the delivered percentage or with the partial pressure. So at lower barometric pressure, for instance, in high altitude, the delivered percentage must be adjusted, all right, in order to ensure that you have the same alveolar partial pressure and the depth of anesthesia, all right? For instance, this is altitude effect. You can imagine at sea level where your atmospheric pressure is 760, all right? And the oxygen concentration remains at 21%. But at 3,000 feet, the partial pressure of oxygen has dropped to 110 millimeters of mercury, all right? And this will then explain why patients at high altitude desaturate very fast. Okay, monitoring anesthetic depth, okay, this explains it further. For instance, you are giving the patient 2% sevoflurane as maintenance, all right, at sea level where the pressure is 760. The pressure of the partial pressure of sevoflurane is calculated at 15. But we realize that at high altitude where the barometric pressure has dropped, all right, the amount of the pressure of sevoflurane you are given will be 10. Okay, although the minimum alveolar concentration has not changed, you realize that fewer molecules of the sevoflurane gets to the brain, and this may, portend the risk of awareness. So what we look at is, although it's easier to use MAC to calculate the depth of anesthesia, what usually matters, especially at different altitude or barometric pressure, is the minimum alveolar partial pressure. All right. So anesthetic effect is governed by partial pressure, not by the percentage setting. So we must always adjust our MAC setting, especially in the environment where we have different barometric pressures, in order to deliver the correct minimum alveolar partial pressure. All right, so Henry's law. Henry's law states that the amount of gas that is dissolved in a liquid is directly proportional to its partial pressure above the liquid. Okay, and this explains uptake and elimination of volatile anesthetic agent. Don't forget that your inhalation agent diffuses from the alveoli to the brain, to the blood, to the brain. So higher alveolar partial pressure will mean more gases are dissolved in the blood with faster induction. During emergence from anesthesia, alveolar pressure drops, the gas comes out of solution, enhancing speedy recovery. And this also explains the blood gas partition coefficient to determine the anesthetic that are dissolved, the amount of anesthetic dissolved in blood. Okay, so the second one is implication of Henry's law is hyperbaric oxygen therapy. So if you're breathing up 100% oxygen at greater than 1 atmosphere, all right, this will increase the amount of oxygen present in alveoli and blood, and this ensure that more oxygen dissolves in plasma. beyond what is carried by hemoglobin. All right, this is crucial in conditions with severe anemia, carbon dioxide monoxide, and even wound healing. Okay, even volatile gases, their effect depends on partial pressure. At higher ambient pressure, lower concentrations are required to achieve the same CNS effect. Decompression sickness, all right, this usually happens to divers, all right, breathing compressed air. And this air accumulates, all right, in the blood and tissues because of high concentration. However, when they're coming out of the water, if the ascent is too deep, the ambient temperature drops too acutely and too quickly, and this leads to nitrogen coming out of solution, forming bubbles, all right, and this can accumulate in joints known as the bends with some neurological symptoms, and they have cardiovascular collapse. Prevention is usually better than cure. So what we do, trained divers know that coming out of deep waters, you need slow ascent, and the decompression will stop, allowing nitrogen to be safely eliminated via the lungs. So Henry's law also explains second gas effect, where a fast absorbed gas like nitrous oxide rapidly leaves the alveoli, decreasing alveoli volume and raising the partial pressure of the second gas. All right, this is what we call second gas effect. All right, so this leads to accelerated uptake of the second gas, speeding induction of anesthesia. Okay, and this is explained by the Henry's law. Why the partial pressure of the first gas drops, that is nitrous oxide, the concentration of the second gas increases, which enhances its diffusion from the blood, all right, into the brain, from the alveoli to the blood and to the brain. All right, we're going to look at the Hagen-Poiseuille equation, which governs laminar flow. All right, we know that laminar flow occurs where flow is smooth and steady, and its greatest velocity lies in the middle of the tube. All right, while it is zero for gases touching the side. Laminar flow normally occurs in smooth walled, parallel-sided channels of greater length and diameters. And this is explained by the equation we see. The flow, all right, the Q is the flow, the P is the pressure difference, R is the radius, H is the viscosity, and L is the length of the tube. All right, the clinical implications varies widely. For instance, from your IV fluid administration, we know that from the Hagen-Poiseuille equation, flow rate depends strongly on the catheter radius. Okay, so if you double the radius of a catheter, you are increasing the flow almost by 16-fold. So large bore delivers fluid faster than smaller ones. And this is important. We need to be careful, especially when we are looking at citing our central line. All right, most central line, maybe the triple lumen or the 5 lumen catheter. All right, they are good because you can give different types of fluid, but flow through them is slower because they have smaller radius. So if you need to give blood or fluid faster, all right, or more quickly, you will need a large bore IV instead of just acting a central line with a low radius, catheters. All right. Fluid viscosity is also explained by this equation. Blood products usually flow slower than crystalloids. So sometimes warming the blood reduces viscosity. So warming blood before transfusion is not just to prevent hypothermia, it's also to increase its flow rate. Okay. Airway management, application to airflow in endotracheal tubes. Airflow resistance is inversely proportional to the radius raised to power 4. So a small reduction in tube diameter, maybe due to secretions or kinking, can increase resistance and work of breathing And sometimes you will see the peak airway pressure of your ventilator increases. Okay, the longer tube, all right, increases resistance. And that's why in pediatric anesthesia, I like to cut the endotracheal tube, okay, to reduce the effect of length on the resistance. So the clinical implication here is you must choose the largest appropriate tube, all right, to reduce resistance to flow. Suction your tubes, all right, because secretions can cause blocked tubes, okay? And in pediatrics especially, you know, there are small changes in their diameter and the diameter of their tubes can have a dramatic effect on airway resistance. All right, blood flow dynamics, okay? My time is running. So let's look at Reynolds number. This determines the gas flow condition, whether it is laminar or not. And the formula is here. So when you have a Reynolds number less than 2,000, it indicates that the flow will probably be laminar. And any Reynolds number greater than 3,000 indicates turbulent flow. All right, so the one on the left is laminar flow, while the one on the right is turbulent flow. All right, turbulent flow will give you unpredictable gas delivery. Okay. Now, airflow in airways, we've talked about this, okay? Helios, which is a mixture of helium and oxygen, has a lower density and therefore reduce turbulence and ease breathing in severe airway obstruction. So patients, especially children with acute airway obstructions, are usually given Helios because of the lower densities it has. Okay. Okay, clinical application, heliotherapy reduced turbulence in upper airway obstruction due to lower gas densities. Bernoulli's principle, okay, we explained this during the question and answer time. So for a fluid, either liquid or gas, flow through a tube, an increase in flow velocity, which corresponds to kinetic energy, all right, maybe due to, all right, okay, due to a constriction will result in decrease in the lateral pressure and potential energy, all right? But remember that the total energy remains the same, okay? And this is seen especially in Venturi effect and oxygen delivery. Look at this, oxygen is flowing, but when it meets a constricted area, the velocity increases, kinetic energy increases, and because kinetic energy increases, potential energy must reduce. All right, and if potential energy reduces, air will be entrained from outside, all right, so that you can maintain, you know, the equal, you know, volume of gas to be delivered to your patient. So this is useful, especially in controlled oxygen therapy, and it also can be used, especially in jet ventilation. All right, you see your manual jet ventilator here. All right, jet ventilation is a method where high pressure burst of gas is delivered to the airway, often through small catheter, to facilitate breathing. Okay, high pressure oxygen is delivered through a narrow cannula, creating a jet stream with low lateral pressure and training surrounding air. This provides ventilation even in small and obstructed airways. Okay, it's also very important in suction and gas scavenging system, nebulizer function. Okay, the Venturi principle relies on application of Bernoulli's principle, where gas flow through a narrow constriction creates a pressure drop. I mentioned this before. Okay, Quanta effect is important, especially in some ventilators, all right, with no movable parts. All right, it describes the tendency of the fluid to attach itself to a nearby curved surface, all right, follow its contour rather than continue in a straight line. Okay, so this is especially in Pelon non-fit 2200 ventilator. This is the Quanta effect. So the flow of fluids prefers to go through a curved surface instead of this, and it is used, all right, to direct the flow of gases in a ventilator. So by conclusion, Understanding the fundamental gas law is essential for safe and effective anesthesia practice. Okay, these principles govern the behavior of gases under changing pressure, volume, and temperature conditions, forming the basis of ventilation, vaporizer, gas delivery system, and patient physiology. All right, these are some of the references. Let's stop here this evening. I was glad I was able to run through it. So if you have any question, any